Welcome to the 20th class of this course. Let me first summarize what we did in past 3 classes. So we introduced the Bessel differential equation. We solved it and we got the Bessel function of first kind. Then we got another solution from the Frobenius method that was basically g of minus px, but we showed that this g of minus p, it's not an independent solution for all values of p. So in that case we introduced a new function that we are calling the Bessel function of second kind, or the Newman function, which is given by this expression. So this jpx and ypx, these are two independent solutions of this Bessel differential equation. Now in this class what we will do is we will introduce another method from where we can find this Bessel function of first kind. So the method is called the generating function. Generating function of Bessel functions. In case of legendary functions also, we have introduced the generating function. So similarly, for Bessel function also, this generating function, which is the function of, let's call it g, which is a function of x and t, that is given as exponential of 1 by 2x times t minus t, and it will generate the Bessel functions in the power series of t to the power n. So if I write this expression, this generating function, in the power series of t to the power n, then in the coefficients there will be jpx, where n is going from 0 to infinity. Sorry, n is going from minus infinity to infinity. So this is how this generating function, this function of x and t, it produces these Bessel functions. Now let me prove it. Proof. So I will show that this expression can be written like this. So our generating function is g of xt equals to exponential 1 by 2x t minus 1 by t. It can be written as exponential 1 by 2 xt or xt by 2 times exponential minus of x by 2t. Now if I expand these two exponentials in Maclaurin series, then what we will get is basically sum over, let's say r equals to 0 to infinity, the summation index, and it can be written as xt by 2 to the power r divided by r factorial times this function, which is, if written in terms of series in the Maclaurin series, then it can be written as, can be expanded as s equals to 0 to infinity, sum over s equals to 0 to infinity minus x by 2t whole to the power s divided by s factorial. Now if I multiply them two, then it will be sum over r equals to 0 to infinity times sum over s equals to 0 to infinity times minus 1 whole to the power s, so because of this minus sign, times xt by 2 whole to the power r times x by 2t whole to the power s divided by r factorial times x factorial. it can be written also as summation r equals to 0 to infinity summation r s equals to 0 to infinity minus 1 whole to the power s. Then this half, if I write it here, then this half will have a power of r plus s. Similarly, this x will have a power of r plus s, and it's divided by r factorial times s factorial. But now this t, it will have a power of r minus s, right? Because there is a t in the denominator here, and for this term the t is in the numerator. So now this is our generating function. Now I want to write it in the series of t. So I want to write it like sum over something times t to the power n, where n is going from 0 to infinity or minus infinity to infinity. This is how I want to write it, and for that I will introduce a new variable n, which will be r minus s. So let me introduce a new variable n, which is r minus s. So in that case, and what we have is r is going from 0 to infinity and s is also going from 0 to infinity. So r should also be greater than 0 and s should also be greater than 0. These two conditions we have. And then if I want to replace s with n and r, in that case I have to write s as r minus n. So in this from this expression of g of xt, I want to replace this x with this r minus n. So now I will write this generating function, and I will consider the case. So I'll consider, let's say, case 1, which is n greater than equals to 0. So I will only consider those terms for which n is greater than equals to 0. That means when r is greater than s. And I will replace this s with n and r. So our summation will be the sum over n, it will be going from 0 to infinity, because I am considering only the cases where n greater than equals to 0. And then the r summation, if you notice here carefully, that s should be greater than equals to 0. So in that case, this r, it should not go from 0, because for any positive value of n, for example, then s can take negative values if r is going from 0. So r should start from n. In that case, s will start from 0. So r should start from n to infinity. For a particular value of n, r should start from n to satisfy this condition, to satisfy this s greater than equals to 0 condition, because here our summation was starting from s equals to 0. And I will replace this s with r minus n. So then we have minus 1 whole to the power r minus n times 1 by 2 whole to the power, so r plus s, and instead of s I can write r minus n. So I will, then it will be 2r minus n, it will be 2r minus n times x to the power, there is r plus s, so it will again be 2r minus n, and divided by r factorial times s factorial. So s is r minus n, so it is r minus n factorial times t to the power. So here there is r minus s, and r minus s I considered as n, so it will be t to the power n. And now you can see that the coefficient of t to the power n is basically this entire summation, this entire term, which is summed over r. So this is the coefficient of t to the power n for n greater than equals to 0, because n is starting from 0. And we want to show that these coefficients of t to the power n, these are basically the Bessel functions of first kind. So that's what I'm going to show now, that this coefficient which is sum over r equals to n to infinity minus 1 whole to the power r minus n 1 by 2 to the power 2r minus n times x to the power 2r minus n times r factorial times r minus n factorial. This is basically the coefficient of t to the power n, and it can be written like this. So that's what I am going to show. It equals to, so now I can so here r is starting from n, so instead of starting from n, I can introduce a new variable m, which is r minus n. So in that case, when if r equals to n, then m equals to 0, and if r tends to infinity, then m tends to infinity. So the summation will be from m equals to 0 to infinity, then minus 1 whole to the power r minus n is m, so whole to the power m 1 by 2 to the power. So in place of r, I am replacing it with m. So in that case, r I can write as m plus n, and if I do that, then it will be 1 by 2 to the power 2 times m plus n minus n, and which is nothing but twice m plus n, right? So it will be 2m plus n times x to the power, so it has the same power, like x has the same power as half, so then it will also be twice m plus n. And now instead of this r, I can r factorial, I can write as m plus n factorial, and this r minus n factorial, I can write it as m factorial. Then it becomes sum over m equals to 0 to infinity minus 1 whole to the power m 1 by this m factorial, I can write as gamma of m plus 1, and this m plus n factorial I can write as gamma of m plus n plus 1, and this x divided by 2, so I can take this x inside this bracket and I can write it as x divided by 2 to the power twice m plus n. And if you can recognize this function, this is nothing but this Bessel function. This is nothing but this Bessel function of first kind. So here instead of p, we have n. So our Bessel function will be here. This is nothing but jn x. So that means for n greater than equals to 0, what we just showed is our generating function that we have introduced at the beginning. It can be written as sum over n equals to 0 to infinity jn x t to the power n. So half of the proof is done. So we showed that it can be written as jn t to the power n for n greater than equals to 0. Now we need to show the same thing for, so case 2, which is for n less than equals to 0. Now I will show the same thing for n less than equals to 0. Now let me write this expression again. This expression, let me write this expression again. So this generating function, we wrote it as sum over r equals to 0 to infinity, sum over s equals to 0 to infinity, minus 1 whole to the power s, then 1 by 2 to the power r plus s, and there is also x to the power r plus s, so I will write them together. So I will write them as x by 2 whole to the power r plus s times 1 by r factorial times s factorial, r factorial times s factorial times t to the power r minus s, and again we want to write this generating function as sum over n equals to, let's say n tends to minus infinity to 0, some coefficient times t to the power n. This is how we want to write it. So here n will be going from, so n will take negative values, n will be going from minus infinity to 0, and for that reason again let me introduce another index, that is n, which is r minus s, and it implies that s equals to r minus n. Here also s need to satisfy this condition, as well as r also needs to satisfy this condition. It should be greater than or equals to 0. Now let's write this generating function, which is g of x t equals to, and so we are assuming that n is less than or equals to 0. So in that case n should be going from minus infinity to 0. And what about r? Because in the previous case, to satisfy this s greater than or equals to 0 condition, we had to start this r from n, because n was taking positive values. So this r should be starting from n for a particular value of n. Otherwise s will be less than or equals to 0. S will be less than 0. So, but here do we need such conditions? Because n is already less than 0. So n is already a negative number. So that means that if I start r from 0, if I don't change the limit of r, the summation limit of r, s will be well above 0, because this n is negative now. So this minus n will be positive. So I can safely write r from 0 to infinity, and then it will be minus 1 to the power. So instead of s I will write r minus n, and then I will write x by 2 whole to the power r plus s. Instead of r plus s I will write 2r minus n. So because in place of s I am writing r minus n, so it will be then 2r minus n, and then it will be 1 by r factorial times s is r minus n, so it is r minus n factorial times e to the power n. Okay, r minus s is n. So now you can see that the coefficient of t to the power n is this term. Okay. So this is basically the coefficient of t to the power n for n less than or equals to 0. And if I write it here that it is going from r equals to 0 to infinity, minus 1 whole to the power r minus n, 1 by r factorial times r minus n factorial times x by 2 whole to the power 2r minus n. Now I will take this minus 1 whole to the power n outside this summation, whole to the power minus n outside this summation, and then we are left with sum over r equals to 0 to infinity minus 1 whole to the power r divided by r factorial, that I can write as r plus 1 gamma of r plus 1 and this r minus n factorial I can write it as r minus n plus 1 and then x by 2 whole to the power 2r minus n. And this minus 1 whole to the power minus n, this I can write as minus 1 whole to the power n. If you can recognize this function, it is nothing but j of minus nx. So j nx was this function jpx, and if I put minus p instead of p, then I will get this. So instead of p I am writing it as n. So if I put minus n instead of n, so here I got this jn, here I got this jn. So instead of n, if I write minus n, then I will get this function. So what we got is basically the coefficient of t to the power n is nothing but minus 1 whole to the power n j of minus nx. And now in the previous class I showed that this is same as jnx when these n are integers. Okay. So what we showed basically is this g of xt that we introduced in the beginning of the class, generating function. It equals to sum over n equals to n tends to minus infinity to 0 jnx t to the power n for n less than equals to 0. And this is the second half of the proof. So what we showed in these two halves, in these two cases, is for n greater than equals to 0, generating function can be written as this, and for n less than equals to 0, generating function can be written as this. If I combine them, then I can write this, that our generating function g of xt, which was exponential 1 by 2 x times t minus 1 by t, it can be written as sum over n tends to minus infinity to infinity jnx t to the power n. So this is a generating function which generates the Bessel functions, for integer values of n, which generates the Bessel function as a coefficient of this power series into to the power n. So these are the Bessel functions. Now there are other methods from which this Bessel function can be generated. One such method is the integral representation of Bessel function, which is written as jnx equals to 1 by pi integration from 0 to pi cos of n phi minus x sin phi d phi, where this n are integers. There is also another method from which these Bessel functions can be generated, which is also an integral, that is jnx equals to half x or x by 2 to the power n divided by root under pi times gamma of n plus half times integration from minus 1 to 1 minus t square whole to the power n minus half e to the power I xt dt. Here n is greater than minus f. So these n can take non-integer values also, but conditioned upon that n should be greater than minus f. So in this way Bessel function can also be generated. So if you want the proof that these are really another method of generating these Bessel functions, then the reference is special functions for scientists and engineers by W. Bell, chapter 4. So today what we discussed is basically the generating function of Bessel functions, and what it does is basically it generates the Bessel functions, as a power series expansion of t to the power n, and in the coefficients there will be Bessel functions. So in the next class I will talk about some recurrence relations regarding these Bessel functions, and then I will talk about the orthogonality of Bessel functions. So that's all for today. Bye.